What we're going to do now is take a look at the graph of our function. So remember, we had the function v of t equals the quantity t minus 10 squared. So that gives us this quadratic looking graph here that's decreasing and concave up, or decreasing at an increasing rate. Now, when we did each of those calculations, let's say our upper estimate, we did 100 feet per second times 2 seconds. Then we did 64 feet per second times 2 seconds. And so on and so forth. What that gives us, what we could represent that by, are these rectangles. Notice that the area of the first rectangle is 100 times 2, or that 200 feet traveled. The second rectangle is 64 times 2, or the distance traveled during the second 2 seconds. So what we're finding is the area of these purple rectangles represents what we found. Okay? Now the total area of all 5 rectangles combined gives us an upper estimate for the total distance traveled during the 10 seconds. We call these left-hand sums. The reason they're called left-hand sums is because the sum is created with the left-handmost point of the graph, and then drawn across gives us the top of our rectangle. Now, if we have left-hand sums, then we must have right-hand sums, and you can imagine the top will be made with the right hand of the rectangle. Well, it turns out our right-hand sums are the rectangles we made when we did the lower estimate. So we've actually already calculated the area of these rectangles. Okay? The area of this first rectangle is 64 feet per second times the 2 seconds, so 64 times 2. Area of this next rectangle is 36 times 2. So on and so forth, and then you can't see the rectangle here because remember this last one had a height of 0, but there's a fifth rectangle here, it just happens to have an area of 0. So these 5 rectangles give us the lower estimate that we calculated earlier, and they're known as the right-hand sums. Here they are plotted together. So we have our left-hand sum, and we also have our right-hand sum. Now the difference between the two, well, the difference in this first estimate between 0 and 2 seconds is basically this purple part up here and on down. Now if we add up those purple parts, we get how far apart our two estimates were. 100 times 2, remember our first estimates when we did 2-second time intervals were 200 feet apart. Okay. What about for 1 second? Well, if you remember, our upper and lower estimates were 385 and 285, so they were 100 feet apart. Well, here they are for the 2-second time interval, here they are for the 1-second time interval. Alright, so notice we're always having this 100 multiplied by whatever our time interval is. So, for 2-second data, it's 200 feet. For 1-second data, it's 100 feet. Now what if the velocity was given every 1/10 of a second? Well, the difference between the upper and lower would be 1/10 times 100, or 10 feet. So we're improving our accuracy. What about every 100th of a second? Well, we'd be multiplying 1/100th by 100, and our two answers, our upper and lower estimate, would be 1 foot apart. So they'd be very accurate. Now, as you can imagine, if we had to do every 100th of a second, that would be a lot of data for 10 seconds. That would be 1,000 points that we'd have to calculate, and it would take a while. But one of the big keys, and what we'll be looking at the rest of this module, is the more measurements we take, or in other words, the more rectangles we use, the more accurate our estimates are going to be. So if it's the case, the more rectangles we use, the more accurate we're going to be. What if we wanted to get the exact distance traveled? Well, think about what happened if we had an infinite amount of rectangles. We'd get exactly the area between the velocity curve and the x-axis. So that's going to be our goal, is to get that area underneath the curve and above the x-axis as exact as possible.